Welcome to the intermediate level NLP tutorial today. We're all at PyData NYC. We all know that. My name is Aditi, and today Eugene and I would be introducing the concept of language modeling. We have structured our today's talk in 5 sections, as you can see here. We'll be driving with the intuition behind language models. What does it even mean to model language that is something so unstructured and something that can be very noisy? In the second section here, we'd be giving you some glimpse of the present applications of language models. In the third section, we'll be diving into one of the earlier known language models, the n-gram language models. The first session did touch upon n-grams and what they really are as well. The first 3 sections are expected to take about 20 to 30 minutes. In the fourth section, we'd be diving actually into an exercise where we'd be doing hands-on work in the Jupyter notebook that hopefully you would have set up by that time. There's a small, tiny Twitter challenge in that exercise part. We do have some goodies to give away for the best tweet, and the details of that tweet would be coming up soon. I mean, of course, in the fourth session, not sooner than that. But in the fifth part here, Eugene would be introducing how the language models are being used today, or what are the new implementations of language model algorithms, not just the n-gram language models. So driving with the language model intuition, I want us to understand that it is something that our mind does very implicitly, very effortlessly. And to understand that part, I want us to play along with me for a little bit. Let's make our mind guess what the next word here would be. Are there any candidates?
Rise. Right.
Rise. All rise.
All aboard.
All aboard. Excellent. So with one word given, your mind could think of like multiple different options here. And all of them might be correct. Some of them might be highly probable. Some of them might not be. But let me limit the vocabulary a little bit. Let's say that you only have these 3 words. Which one would you pick?
Models.
Models. Well, that also, in this case at least, becomes quite obvious because you have all here. You're expecting a plural. There's no other plural. You pick models. What next? Are. Well, that's a verb, so perfect. They are, indeed. Let me throw in some more context knowledge here. This is a famous saying by George Box. He wrote it in 1979, as far as I know. But what do you think where this sentence is going? Excellent. Well, so what your mind really did here, as you would have already gathered, you used the past word to predict the next word amongst so many different, which could have fit that particular space. So it uses the probability of the next word using the context. And in the second case here, you were looking at the last 2 words, and so on and so forth. And putting it in a little bit of a mathematical way, you say that probability of models here in the first space was greater than seeing probability of word given all. And in the second one here, probability of seeing are given all and models was more than the probability of is given all and models, just because they were plural. Now, what you just did was essentially learn a probability distribution over sequence of words. And that is what essentially a language model is. And if your algorithm is good enough to learn that probability distribution, it can also answer questions like the ones you just did. And with this, I'll hand over to Eugene, who'd be talking about the present applications.
Thank you, Aditi. And so now that we've kind of gotten a sense of how language models work, we'll now dive into some of the applications of how they're actually used. And so where are language models used today? The short answer is almost everywhere in NLP, actually. So almost all of the state-of-the-art algorithms nowadays all have some sort of language model behind them, backing them. And so these things range from things like sentiment analysis or entity detection. And some that we'll be going into a little bit deeper in this talk will be autocomplete, translation, and text generation. So to start with autocomplete, you might be familiar with this application from things like when your phone tries to guess the next words you'll be saying or in search engines. And how it works behind the scenes is actually very similar to the exercise that Aditi just led us through. The language model here is basically trying to figure out, based on the previous words that you typed, what the next words you'll be typing are. Another example of where a language model plays a pretty big role is in translation. And so to see how this happens, let's say that we want to translate the French phrase, Le Grand Chien Rouge et Clifford, into English. So the first thing you might want to do is actually just figure out, hey, what English words do each of these French terms correspond to? And so doing a word-for-word translation, we'll get something like, the big dog red is Clifford. But now that we have this kind of one, the next question would be, what order should we put these words in? Should we put them in alphabetical order? Maybe an order like this? Or something like that at the end. And so this is where a language model becomes really useful. So if you recall the definition that a language model is a probability distribution across a sequence of words, we can use a language model to assign a probability to each of these candidate sentences. And hopefully the language model would tell us, hey, the big red dog is Clifford is the most probable sentence of the bunch. And from there, hopefully it'll give the translation model overall some information that maybe that particular sentence would be the most likely translation. And so here, if we just look at a quick formula for how a lot of the traditional translation models have operated, you'll see that the language model plays in here through this last term, where it kind of gives some indication for, hey, we got candidate English sentences, and which one of these is the most likely. Now, the last one I want to go into is a fun example through text generation. And so once you've kind of gotten a model for how language works, you can actually start using that model to generate arbitrary text as well. And so this is actually exactly what someone did online. And so what this person did was they actually took a language model and trained it on a bunch of recipes. And then they asked it, hey, spit out a random recipe for me now. And so see, yeah, it kind of makes sense. We're making small sandwiches today with, we got some ingredients, some instructions. But of course, you'll notice that some things might seem a little bit off, like putting some peas into quarter-inch cubes, or one-inch, not really sure what that is. Now, some researchers in MIT actually took this one step further. They trained a language model on a bunch of CS papers and asked it to produce a new paper. And so this is actually the paper it produced. And so you see, again, it kind of makes sense. It has title, abstract, a lot of jargon in it, mentioning NP complete, stuff like that. And apparently this is what some other people thought too. This paper was actually accepted into a conference. And though it was later redacted when they found out it was actually generated by a machine, I think that kind of speaks to the power that these language models have. And so next I'll hand it back to Aditi to talk about a specific language model algorithm, and also in the exercise section we'll actually start to generate text of our own as well.
All right, so we'll be diving into one implementation of language models, which is n-gram language models. And this is not to drive the motivation of you creating your own research papers and submitting, but hopefully we'll get a glimpse into how one of the earliest known language models were created. We would not be touching any of the neural network language models. We're leaving that for the third session here. But let's dive into n-grams for some time. As with any language model, n-gram language model is also trying to predict the probability of a sequence of words there. So going back to our sentence that we've been working with, let's try to figure out how n-gram language models would work if they're trying to predict the probability of all models are wrong. Taking a step back, most of us would already know what n-grams are, but just for the recap here, if you take one word at a time, that's called a unigram. Bigrams, you're taking pairs of words in your sentence. And for the trigrams, you're taking 3 words at a time, and that's called a trigram. So moving forward, n-gram approach, we have categorized the n-gram approach into 3 tricks. The first one here is you convert the joint probability into conditional probabilities. So by that, I mean you start with the joint probability of seeing all of those words together and convert it into a conditional probability equation here by saying that, okay, I want to see the probability of models given all, which is what was the first question asked to you. Then you add probability of R given all n models and multiply it with the probability of wrong given all models R. So essentially probability of each word given all the words prior to that. Trick number 2, which is essentially Markov chain approximation, as some of you might already know. You approximate the history. So instead of looking at all the words before that particular word, you only look at some of them and you say that that's good enough for me to predict the next word. In this example here, I'm only taking the word before the probability of my given word. And because I'm taking 2 words at a time, for instance, model given R given model, and not everything that existed before, this is known as bigram language model, taking 2 words at a time. Trick number 3, slightly nuanced, but in order to capture the start and the end probabilities, you add start and end tokens. So your equation starts looking something like this. Can somebody say why would we want to do something like that? I mean, I think I already answered it, but can somebody explain this to me?
Easier for calculating conditional probabilities in the past, that NumFOCUS is more relevant.
Yeah. No, you need that. So essentially, the start and the end token helps you understand what are the probable words that a sentence can start with, right? The first one here, the probability of all given S. And then here, the end token helps you understand where can a sentence probably end. So for instance, the probability of this sentence ending in R would be lesser than probability of this sentence ending in wrong. So that's what the end token gives us. So that was trick number 3. Combining all of them together, convert the joint probability, which is what the definition of language models is, to conditional. Approximate the history. Instead of taking everything behind it, you take 1 word or n words, n minus 1 words, and then you add the start and the end tokens. Combining all of them together, you get a formula that looks like this. In this case, we are only doing 2 words at a time, so bigram language models. But diving a little bit deeper into one of those terms here, what does probability of wrong given R comes down to? And that is essentially counting at the end of the day. Based on the corpus that you're learning your language model on, probability of wrong given R would be approximated by count of R wrong divided by the number of times that the word R appeared in your corpus. By this time, I have given you every tool essentially that's needed to learn an n-gram language model. And I want you to give some thought on what happens when one of those counts goes to 0 or is not present in your language model or in the corpus that you're learning your language model on. With this, I will hand over to Eugene, who would take you through the exercise.
All right, so now is to everyone's favorite part, the exercise and the Twitter challenge. For this exercise, we're going to be creating our own bigram language model, and then I'm using it to generate some text of our own. And so if you haven't already, if you could clone or just pull this GitHub repository, and then we'll want to start off with the notebook titled Language Model Tutorial. And then I'll also kind of take a minute to set this up for myself as well, and we'll give you a few minutes to set up.
I will be around in case somebody is having any setup problems. Please feel free to ask questions. I'll be moving around. have your notebook set up, please give us a shout out or raise your hand so that we know we're ready to go forward.
So, and can everyone see this okay? It's big enough.
Check that side as well. How are people doing here? Good.
All right, so why don't we get started? So the first cell here is just a containing a lot of useful imports that we'll be doing, so kind of just run it. Nothing too crazy going on here. Two functions that will just be pretty useful later on is one to flatten a list. So if you have a list of lists turning into a 1D array of lists. And the other one here that we also define is one to pretty print tuples. So we'll be working with a lot of tuples in this notebook because to store like the bigrams and trigrams. And so just finding a way of printing it in a nice way. So we'll be defining this function here. So to be able to train a language model, kind of like as Aditi mentioned, the first thing you need is a corpus of example, in this case, English text, to kind of let the language model know, hey, this is what English looks like. And so the first corpus that we'll be working with is one called the Brown corpus. It's a collection of a lot of English language text from about 500 different sources, and they've actually grouped it into 15 different categories as well. And so we'll again be using NLTK to actually get this data set. And so they actually provide a really convenient function to get the sentences from this data set as well. So all you have to do is call brown.sense, and it'll actually return an array of all the sentences in the Brown corpus. And so here, just printing 5 example sentences, we'll see something about the Fulton County Grand Jury. So maybe like looks like a news article talking about a court case of some sort. Looking at one single tokenized sentence a little bit more as well, we'll notice that it actually comes in the form of array of words or tokens. And so this is actually very convenient because for n-gram language models, we need to know what like a word or a token is. And so this form that NLTK kind of already gives it to us kind of alleviates a lot of the pre-processing that we would have to do ourselves. And if you are interested in actually learning how to build this from scratch, in the appendix A, I believe, we actually have an example where we download the brand corpus off a URL and do a lot of this tokenizing and separation ourselves. Some things that I just wanted to know about this tokenizing as well is one, you'll notice that NLTK decided to remove the punctuation from the words. And I think especially for n-gram language models, this is pretty useful because you don't treat place period as a token. You actually treat them separately. So whether place is at the end of the sentence or middle of the sentence, it's still the same word. Another thing is just to note that there are many things that we actually could have done to pre-process this text more, such as lowercasing all the words or stemming or removing punctuation. But just for the sake of this exercise, we'll just leave it as is from NLTK. All right, so the first step we'll want to do, and kind of the key to building an n-gram language model, is knowing how to count. And so we'll warm up with kind of answering a slightly simpler question, which is, hey, what are the most common unigrams that show up in our corpus? And so to do this, we'll use a Python object count a counter. And for those who aren't familiar with it, a counter is kind of like a dictionary, except it has a default value of 0 when the key doesn't exist. So it's essentially built to count things. And it also has a really convenient most common function to get the most common elements from it by its counts. And so to do this here, in this little snippet of code, what we're doing is we're first creating a counter object. And then we're iterating through each word in each sentence and basically incrementing how many times we've seen that word. And so going down here, we'll see that, oh, our data set has 56,000 unique words in it. And a lot of the top words actually make a lot of sense. Things like the, of, and, like very common English terms. And another thing we can do, and I won't go into this code too much, but it's mostly plotting, is we can actually plot the distribution of these words as well. And this is going from most common to least common. And this plot actually shows a phenomenon commonly known as Zipf's law, which says that the most common words show up exponentially more often than the less common ones. And so you can kind of see that in the shape of this graph here as well, where it has a really long right tail. And now just go into a little bit of a short aside, kind of as we're exploring this data set. I think an important thing to bring up as well is just the notion of stop words as well. So stop words are often words that people, when they're doing some NLP, will sometimes think aren't as interesting per se. And though there's no strict definition for what a stop word is, people have kind of created their own lists, including NLTK as well. And so here we can see some examples of, they think words like I, me, myself, aren't quite as interesting. And so what we can do here is actually kind of take these counts again, but take out the stop words and also punctuation to hopefully see some of the more interesting words that characterize our corpus. And so in this particular example, you might see that a lot of these words actually aren't too interesting per se as well. And I think that kind of just speaks to how general of a corpus the Brown corpus is. And again, we can also take this list and create another plot as well. And what's interesting here is even after taking out the stop words and punctuation, it's still a pretty exponential looking curve here as well. So now that we've gone through counting unigrams or words, let's move into counting higher levels of n-grams, starting with bigrams. And so to be able to do this, we'll actually need to make a slight modification to our unigram counting code. And as a reminder, for when counting bigrams, for a sentence like the red dog is Clifford, we'll want to, the bigrams in that particular sentence would be the red dog is Clifford, and Clifford period. And then kind of as Aditi mentioned, looking at if we add the special sentence end and sentence begin tokens, we'll also get 2 additional tokens here. And so the code we have here is actually largely similar to what we had before, except we do we actually track what the previous word is so that we can start putting these bigrams together. And so again, we're iterating through each word of every sentence. And we're incrementing the bigram counter with the bigram of the previous word with the current word. And then we update the word to the what the previous word was. And then in addition, we'll also actually be adding an additional bigram to capture that sentence end thing. And then also resetting the previous word to sentence begin once we finish going through a sentence. And so we'll see here that a lot of the top bigrams are, the top bigram by far is a period with a sentence end token. And that actually makes a lot of sense because a lot of sentence will end with a period. And then we'll see things like of the sentences like to start with the as well. And so just looking at this code again, I think doing this by hand is just really instructive for knowing how do we count bigrams. But of course, writing it from scratch each time, we're expanding this to work with trigrams, fourgrams, and so on, can be quite complicated. You'll notice that there are a lot of corner cases, so maybe if you're off by 1, you'll just get some completely wrong answers. And so conveniently, as will be a theme throughout the rest of this notebook, NLTK provides a function to do this for us. It's called n-grams. And so what this function does is it takes the sentence as an argument and kind of your n. So here with bigrams, our n is 2. And then we also tell it to pad it on the right and the left with the sentence end and sentence begin tokens. And you'll kind of notice the output here again is exactly the same. All right, and now as a quick exercise, maybe I'll give you 30 seconds or a minute just to answer the following question for what are the most common trigrams in our data set now. And I would recommend using the NLTK implementation of n-grams rather than writing your own. Now, yeah, bringing everyone back, we'll also just go through this exercise really quickly together. So basically, yeah, I guess usually in computer science, it's not very good to copy paste code. But for the sake of exercise, we're going to do that here. And basically, we can take the same code that we had before and just make a quick find and replace to just rename our variable to a trigram counter. And then if we change the argument from n-grams from 2 to 3, this will give us the top trigrams that appear in our corpus. And so looking through this corpus again, we have some pretty familiar candidates. So ending a sentence and beginning a sentence with the are both appear as the top 2 again. But one question that's kind of food for thought is why don't the top bigrams show up in the top trigrams? And so if you look at the top bigrams, you'll notice that not all of them show up as candidates for what the top trigrams are. And so does anyone have any ideas for why this is the case?
I mean, it seemed to double pad things at the beginning and the end. So if the first word, if the last word's period, I mean, period end to end shows up.
Mm-hmm.
But so many things are at the beginning and the end of, and like of doesn't rank once you include all the beginnings and the ends.
Mm-hmm. Yeah, that's basically it. And so as you kind of notice, like a lot of the beginning and end tokens show up a lot here. And I think, it's very common to see certain punctuation ending and beginning sentences a lot. Oh, yeah.
So when I look at the first one, so a period and an end, that makes sense.
Yeah.
But then I would expect a beginning, like on a trigram. So why I guess what I don't get is why are 2 ends showing up together there in the trigram?
Yeah, and that's actually an artifact of kind of how we tokenized our
May I have
sentences.
your attention, please? May I have your attention, please? This is the building fire and life safety director. We have received an alarm from the cellar and we are making investigations. Please stand by for further information.
All right. Sounds the same as the fire safety director in our building too.
Yeah, that's a question.
Oh yeah. Yeah. Actually, so yeah, it's since we did only one sentence at a time, we didn't give it a notion that we're chaining the sentences together. So it'll actually pad it with 2 start sentence begin and sentence end tokens on each side.
Oh, okay.
Yeah.
Okay.
We're building a trigram language model here. So the trick 3, which was like start and end tokens, there we were doing only 1 at a time because we were building a bigram language model. Here, because we're doing trigram language model, you want to go from the start of the word to behind, right? And for the end, so it's like padding 2 on both sides.
Yeah.
Right.
Yes.
Does the double space, would a double space get captured in the bigram?
A double space. That's interesting. So for
May I have your attention, please? May I have your attention, please? This is the building fire and life safety director. We have concluded our investigation into the alarm signal from the cellar. We have discovered a system malfunction and it has been corrected. Please resume normal business activity. Thank you.
all right, we're safe.
You're saying
Yeah.
he had a question.
Yeah. So for that question, part of what how NLTK actually pre-process their text is I think they probably used the space as a tokenizing. So they probably split on space so that an empty space is never a token here. But I imagine depending like if you actually did want to preserve that.
Well, but it's being captured, the single space is being captured in the bigram, that's why I asked.
That's the start symbol.
Oh, this is a sentence began and sentence. Is it this token that you're referring
Okay.
to? Yeah.
All right, gotcha.
It's representing the start with the HTML type tags.
Sure.
Start and the
But I guess I don't want to beat the dead horse here, but so if we would build like a quadgram, right? We'd expect the same, probably like a period shows up and then 1, 2, 3 sentences.
Yeah.
Yes, because
Exactly.
it should, ideally.
So this is, okay, so that's the artifact there where it's not really the 3 most common words.
Exactly.
Right. Yep.
So you might want to remove those words, just like you did remove the stop word. And also, aside on stop words, I'm observing that some of you are having problems in downloading NLTK stop words. Please bypass that and move forward and assume that you cannot get rid of stop words for now. That's a side effect of NLTK download library. But coming back to your question, sir, if you remove S and \S, your most common words would come.
Yeah.
The real ones would come up. Bubble up.
Yep. Yeah, and we can actually, for risk of live demo, we can try that real quick by just removing the padding as well and seeing what comes out.
We're only doing the padding because we're going to do some really cool stuff with it in the moment.
Yes, exactly. Mostly for the language model. Yeah, so actually, yeah, this is kind of cool. You'll see like the United States is pretty common. Of course, some punctuation as well.
The counts went down too, if you see.
All right. Cool. So moving forward, once we have the ability to count these n-grams, we can actually start creating probability distributions from them too. And so kind of just focusing on the bigram example where we're going to be creating a bigram language model, we can approximate the probability for a word given its context by just looking at the previous word. And kind of as Aditi mentioned earlier, you can figure out what this probability is by taking the counts. So here we're basically taking the count of how many times the bigram shows up and dividing it by the count of how many times the context word showed up. And this approximation for the probability is actually also known as the maximum likelihood estimator for those that are familiar with that concept. And so one slight nuance here is actually to be able to do this well, we need to store a bigram slightly differently. So instead of counting each bigram directly, we're actually going to create a map to map each context to the number of times the word follows that context. And so to do this, we're creating a dictionary here called bigram context counter. And then, like before, for each sentence, we're going through each of the n-grams, or bigrams in this case. And then if that context word, so the first word there, doesn't exist in our dictionary, we're going to create just a new counter object to start storing how many times that word has appeared. And then we're just going to increment it like before. And so to kind of start motivating why we're storing it this way, with this storage mechanism, we can easily start answering some more interesting questions, such as what are the most common words that start a sentence? And so can anyone tell me what we should put in this little to-do block here?
Just going back to what this data structure is, we have a map starting with the context and what are the other words that it exists with.
Yeah,
Absolutely.
exactly. So if we insert the sentence begin token here, this will give us the most common words that have been used to start a sentence. And so you see words that we kind of expect like the, he, it, and so on. And just going back to this equation here, we can actually start use these counts to derive a probability distribution. And so here's a function called getWordProbabilities that kind of takes in that context counter. And then what it does first is it computes the total counts by just adding all of the counts. And that gives us the denominator here. And then what it does is it creates a dictionary mapping each word to its probability by dividing the count of the bigram over the total counts in here. And so kind of running this, we'll basically see something very similar, except now the counts have been converted into probabilities. And so next, since this data structure is actually quite important, I'll give you maybe another minute or two just to go through some of the next exercises to see how you can use the data structure to answer some other questions.
have answered the first one here. Eyes, yes. That is one of the ones that did appear in my corpus too. Second one.
Four. Oh, that's for the blue sky.
Yeah.
There was a slight reorder. Alright. Yes, running ahead. Yep, and so bringing it back, yeah, just doing it here overall, you can see that by putting the words that you're looking for into these blanks, you can get like, hey, these are the most common words that come after the word blue. Or this is, so blue seems to have appeared 97 times in our corpus, and blue sky appeared 4 times. And so I guess there are 2 ways of kind of deriving the probability that sky comes after the word blue. One is just taking the word number 4 and dividing it by 97 here. Or as you can see, we can also, again, just take advantage of that function we wrote to get a map of all the probabilities. And so here, sky comes after the word blue about 4% of the time. And so actually going through this whole exercise, what we've essentially created now is our very own bigram language model. And so to make that clear, we're actually just going to rename the variable really quickly as well. And we're just going to suffix it with the phrase manual just to kind of indicate that this is one that we constructed by hand. And just a quick clarification here too, even though the object is a counter and a language model is really in the end assigning probabilities to different sequences, you can use, as we've seen, you can use these counts to derive those probabilities. And so this data structure that we have here is a core of what we need. And so recalling that the goal of a language model, again, is to be able to assign probabilities to a sequence of words, we'll show how we can do that with the language model that we just created. And so here, let's say that we wanted to see the probability of seeing the sentence, "The blue sky is beautiful." What we could do to get that is first getting all the bigrams from this sentence, again using the NLTK ngrams function. And then basically we kind of start a rolling probability with 1, and we update, basically take the product of all of these different conditional probabilities together by using the getWord probabilities function, similar to what we had up here. And so doing that, we actually get that the probability of seeing the blue sky is beautiful is some very, very small number here. And so yeah, one trick that people use often to help deal with these very small numbers is also to take the log. And so now you can see that, oh, the log probability of the blue sky is beautiful is negative 29.1. And if you're familiar with as well, to avoid the floating point error, one thing that you can do when you're computing if you wanted to compute the log probability directly, is to actually take the sum of the log probabilities, because it essentially multiplies all of the insides together. And so now that we've kind of gone through the exercise of implementing a language model from scratch, let's see how we can do it with NLTK. And so with the NLTK's implementation, there is a little bit of time just to understand kind of what their APIs look like and how they accept their training data. And so here, the NLTK called their implementation the MLE, which is short for, again, maximum likelihood estimator. And so the constructor takes in an argument n that specifies what the n-gram length you want to use is. And as you'll note here, we actually haven't trained anything yet, so the vocabulary size is still 0. Now to add some data into the NLTK language model, we'll actually have to give it in a very particular form. that they actually have a function called padded everygram pipeline that provides it. And so this function returns basically two objects. One is the what we call train text, is a list of all of the, in this case, unigrams and bigrams that came from our corpus. And the second argument is essentially the set of vocabulary that it derived from our corpus as well. And then calling the fit function, it basically uses these bigrams and unigrams, as well as the vocabulary to basically do what we did above to create the language model. And so once we've trained the language model, we'll again see that, oh, it's about 56,000 words in total. And so with this language model, we can again answer some of the questions that we saw before. And so one thing here, one neat trick as well, is if you want to know what functions a given object has, you can use the dir function that will actually print out all of the methods that a Python object has. And so a lot of these start with the double underscores, which are just kind of like built-in functions. But here you'll see the ones that they've defined themselves as well, including useful ones like counts, context counts, entropy, fit, and so on. And some of these we'll find pretty useful. So the first one we'll use here is just the counts. And so running this, we again can answer, hey, what are the most common words that come after blue? And yeah, just one small nuance here is that you'll notice that the way we specified blue in this tuple is kind of weird. The first thing in the tuple is the string blue, and the second is actually just empty. And this is more of an artifact of how Python has defined their tuples, where basically if we get rid of this comma, it'll actually interpret it as a literal string, I believe, in this counts object. And so having that comma there somehow explicitly tells it that, oh, this is actually a tuple, and so we'll want to get the context. And again, we can also compute probabilities like before, and so they provide a very convenient function called score that basically converts. So if you wanted to see what is the probability that sky comes after the context blue. And again, doing a really similar piece of code from above, except just replacing the probability down here with the NLTK score function, we can again compute the probability that the sentence, the blue sky is beautiful. And here we'll notice that it's actually exactly the same as the one we did above. All right, so now that we've gone through how we can create these language models, we'll actually use it in an application of generating different sentences, like the examples that we presented before. And again, like before, what we're going to do is we're going to start off by implementing this manually again, just to get a sense for how it works. And then we'll show how you can do it with NLTK. So to start, we're going to introduce something called the greedy method. And so you can imagine that one way you could try to generate these sentences is start with the sentence begin token, and then ask your language model, what is the most common word to show up after sentence begin? And then just keep doing picking the most likely word one after the other until you get to a sentence end token. And so we're going to call this the greedy method here. And this is what it produces. So can anyone kind of volunteer for why they think this happened, or what do you think is wrong with this approach?
What's deterministic?
Yep. Yeah. So it's basically deterministic, and in this case, it actually ran itself into a loop as well. So like and the same time seems to just keep looping over and over on itself. And so to make this a little bit better, we're actually going to use a little bit of randomization. And so the method here is pretty similar to before, except now we can repeatedly compute the probability of a word given its context, and then select a word at random from that distribution. And sorry, there's a slight mistake here. This should be, since we're doing a bigram language model, just a single word context. And then we can repeat that until we get the sentence end token. And just going into the code a little bit here, the get random next word is pretty integral to this function. And so what it does is it gets again, the word counts from the object that we created before and gets a set of probabilities as well as the vocabulary. And then using the function np.random.choice from NumPy, you can give it the vocabulary that you want it to select a random element from. And you can weight each element by the probability. So it basically gives you a random word based on the probability distribution. And so using this, we can actually start generating random sentences. And some notes on this arguments. So here, again, it's just the language model that we created. And then the text seed is just an option if you wanted the sentence to start with a particular word, like the, or I don't know, you really like bananas or something like that. And then you can also give it a random seed as well. So this is kind of just to control the random number generator if you want to determine, produce deterministic results. And so, yeah, through this little bit of code here, we're basically starting with a context of the sentence begun. And then if we do have a text seed, we kind of replace it with that. And then we just iterate until we get to the sentence end token. And just to run through a few examples here. So for the first one, we seeded it with the word the, and so it says the Odyssey is boss. So I guess they really like the Odyssey. And here, just seeding it with nothing, it started the word with like someone laughed with its associated, I don't know, textile machinery and some boats.
This is N 3 grams?
Bigram language model. And again, just we can play with this some more. So like we can try changing the random seed as well, just seeing kind of what sentences it produces. Yeah, so it has a lot of Pearl of Industries. Yeah, so you notice that it like kind of almost makes sense, but like definitely not quite there. And actually, if we put in our favorite programming language as well, you actually notice that it gives an error. So it says, hey, this n-gram model has never seen the word Python start a sentence before. And so this kind of ties in a little bit into the example that Aditi was mentioning about before, where if our model has never seen a particular bigram before, or in this case, the word Python starting a sentence, it just won't know what to do. And so there are some ways of getting around this, a technique called smoothing. And so I won't go into it here, but there's an appendix as well that goes into that if you're interested. And finally, to finish, just showing a quick example of how you can do it with NLTK as well. And it's actually really neat. So NLTK, again, has a function that takes in a text seed and a random seed as well. And you just have to call the function generate. And you can tell it how many tokens you want to generate as well. So we'll just do 50 to be safe. And then this slight for loop here, again, is just to basically iterate over all of the generated tokens until we get to a sentence end token, just so that the sentence that's printed out looks pretty. So here, yeah, I guess another example that it produced.
Young adults are less often heard.
Yeah, a standard. Yeah, so maybe it could be quite deep as well sometimes.
Spit diagrams.
Yeah. All right. And so now we're done with this notebook. And so if you could open up the Fun and Language Models notebook. So I actually won't be going through this notebook with you, but maybe I'll probably give like 5 to 10 minutes or so.
5 to 10 minutes or so, go through this one. The exciting part is towards the end of this, if you want to scroll over there and...
Yeah. And then, yeah, so basically this notebook will kind of go through the effect of changing the n-gram length, how it affects the sentences you generate, as well as changing the data set. And then, of course, the exciting part is our Twitter challenge. And I think I'll let Aditi kind of introduce that.
So here we are providing you a framework, a skeleton of things that you can do to play with different NLTK corpora. Is that the link?
Yes, actually.
That's the link that you can click to play around with different corporas that you want to look at.
Yep, so it actually contains a list of all the corpora that NLTK already has included. And so it includes things like a lot of classic literature. I think it also has like online dating profiles too, so if you want to make your own for those as well.
Can be tricky, be careful with that one.
Yeah.
And then once you pick what sentences you're interested in and the n-gram length that you want to experiment with, you would be able to create your own language model and then generate as well. So essentially whatever we went through is concise within these 3 cells here. Although to run these 3 cells, you would need the top 2 cells of this notebook, which will help you import all the required libraries as well as run some of the prettifying functions that you might need. Yeah, and please make sure that you are tagging your tweet. Okay, you're tweeting the sentence that comes out of your language model. That's the ask, essentially. And keep trying until you get something that you're happy with. Please tag it with 2 sigma and the hashtag. This is the hashtag that will help us find your tweet. If you do not want to tweet or do not have a Twitter account, please email it to Eugene. Eugene's ID is right here. And you have about 15 minutes.
Yeah, 10, 15.
10-15 minutes to go about doing that. So find the corpus that you're interested in, choose an n-gram length that you feel will be appropriate for the corpus that you're working with, and then make it generate a sentence that you've been doing all along, but now you'll be doing it from scratch using NLTK.
Yeah, and for our prizes, we'll be giving away these 2 sigma Nalgene bottles with a custom 3D printed keychain inside. And yeah, these you can't get from the swag table, so yeah.
I 3D printed them yesterday. That's like my first 3D printed batch of things.
Oh yeah.
Yeah. this, that'll be easier for us. NLTK is a tricky They have multiple ones. These are the ones from web and chat checks.
Oh,
Right? This is the brown corpus that we were working with. And this is the news corpus, the Reuters data.
So if I want to put this one,
You do something like that. Yeah.
or so those are the field ID. Or just characters, no field IDs. I think field IDs. Or field IDs. I think that's right. File ID.
And tag it with PyData.
Sorry about that.
If you want to generate, you would be cautious of the fact that it will be learning generic pattern from different websites. If you want it to be used for technical analysis or something more specific, you would be cautious of what data you're inputting into learning. For that would be required. It's a trade-off. It depends what your pipeline is, like where your language is used for. Oh yes, absolutely. So this can also help us tag the score that you get from the language model can be used for understanding whether a particular sentence is coming from the first. And then you can use that score to figure out, yes, it looks more like coming from news articles, or it looks more like it's coming from, right? So So 2 minutes, heads up. Do we have any submissions here? Oh, awesome. Well, it seems like people have multiple ones here. Do you want to write the submissions? So we will let you work on that, but moving forward, we have 3 main takeaways from this exercise, and something that I was just talking about. Number 1, that a language model is essentially all about counting. For the formula that you're seeing here, which we generated using the 3 tricks, all of these parts come down to doing these counts from the corpus that you submitted into the language model. But the question was, what happens when your model has not seen the word before, and you're trying to ask, what is the probability of seeing all models are gobbledygook when that word never really existed there? That is where the concept that Eugene touched upon called smoothing comes into picture. Here I'm introducing just one way of smoothing, which is Laplace smoothing plus 1. You can choose to do plus 1 or plus n, or for that matter, even fractional counts can be added. But what smoothing essentially does is that it takes the counts of the known and unknown words, here gobbledygook is at the bottom, and adds 1 to it. And as such, what it ends up doing is it assigns some of the probability mass from known words to unknown words as well. Because here, although the chances of seeing all models are gobbledygook is very, very small, it should not be 0. It makes grammatical sense. So smoothing here, which is, as I mentioned, one of the ways of handling smoothing is plus 1 smoothing, applies some counts here and assigns the probability mass to gobbledygook as well. Number 2, n matters. And there's a trade-off essentially. If you keep n quite small, you're making your language model quite generalizable. If you make it larger, if you have, let's say, if you're picking 5 words at a time, they start becoming more specific to the corpus. So let me throw in some examples here. For instance, when you have a unigram language model, it's essentially just throwing out one random word at a time. It looks like English because it was learned on English, but the sentence on a whole is not making much sense here. Now, on the same corpus, when you increase your n to 2, that sentence is looking much better, but still not making a lot of sense. Trigram is when it actually starts throwing out some nice looking sentences here. Can anybody guess what corpus this is? Shakespeare, absolutely. Oh, sweet prince, Falstaff shall die. Awesome. And then if you train a 4-gram model here, do you think that this is the best? Is that the one that we want to go ahead with and use it in our following pipeline? Maybe not, because now what's happening is it's probably picking sentences as it is from the corpus and throwing back at us. Takeaway number 3, the corpus matters as well. So here what you're seeing is comparison of trigram language model of Shakespeare versus Wall Street Journal. And although the n is constant in this example, the sentence it is throwing out for Wall Street Journal is looking like a news article. And if you focus on the underlying part here, it's trying to say that, okay, rates of interest are soaring in Mexico. Before that, it's also trying to say $99.6 billion. It's trying to throw in some numbers and making sense doing that. With Shakespeare, again, this was the previous example, just here for the comparison. Takeaway number 3 is essentially that corpus matters. What you learn your language model on matters. Now, yes, you have learned your language model, and you have n to choose from, you have the corpus to choose from. How do you evaluate a language model as good? And that really depends on how do you define what best is for your application. Researchers have divided the evaluation of language models into 2 categories: intrinsic evaluation and extrinsic evaluation. In intrinsic evaluation, what ends up happening is, let's say that you had 2 language models here, Shakespearean and Wall Street Journal. Those are the probability distribution. You use these language models to predict what is the probability of an unseen sentence by that language model. So all models are wrong. Let's say that this was a sentence that both of these language models had never seen before. And we pass it through this framework, and I'll be coming to that later on, but essentially you pass it through this framework and see which of the 2 models is doing better. Now, coming back to what this framework is, I am trying to see which of these 2 models has a higher probability of seeing all models are wrong. And perplexity here is nothing but probability normalized over the number of words. And as the name suggests, a higher perplexity is saying that, oh, I'm quite perplexed looking at this sentence, and I'm not as likely to predict that this sentence is coming from the corpus that I was trained on. So perplexity of Shakespeare would be something around 5100. This is for demo purpose only. And perplexity of Wall Street Journal, maybe because it has seen exact same sequence of words in its corpus before, perplexity would be smaller. Coming to the extrinsic evaluation, that is also a method of evaluating language models, but instead of using the perplexity measure or the probability measure, you pass your language model through an extrinsic task. And that extrinsic task can be anything. Sentiment analysis, sentence completion, maybe checking for spellings. And then you see which of the two models is doing what we expect it to do. And for here, Shakespeare might say that I don't know what to do with this sentence, and Wall Street Journal, because it has seen wrong in negative connotations, might give it a negative sentiment there. So coming to the constraints of language models, as some of you might have already gathered what's going on here, language models cannot work in long-range dependencies, which by the definition of language is present in any sentence. For instance, here, all models are wrong, but some are useful. Models here existed at the beginning of the sentence. And some, which also refers to those same models, was at the end of the sentence. And to capture that dependency, you would have to increase your n to 5. And once you increase your n to 5, you're now like overlearning or overfitting to your corpus that you had submitted. The second constraint here that I want all of us to take away is the number of parameters here increases exponentially as you increase your n as well. So the number of unigrams in Shakespeare model we checked was around 9,000. The total possible bigrams would be about 80 million. And that number, as you're seeing, exponentially grows as you increase your n-grams. So the number of parameters that you'll have to learn to create a language model would be quite high as well as you increase your n. All right, and with this, I'll hand over to Eugene for the present state of language models. This was n-gram language models.
All right, I was just looking through some of the submissions, and I have to say they're pretty good. So I'm very excited to share some of them. Before we get to that, I just want to give a quick share on kind of the current state of language models. We'll be talking about two things mainly. One is just how neural networks are used with language models, as well as some ethics as well. And so to start, as early as 2002, some people have started exploring using neural networks to train up language models. And this approach has actually been proven to be really useful. And almost all of the state-of-the-art language models being produced today are neural network-based, including things like Elmo and BERT. And one really powerful thing about these neural network-based language models is that they create a byproduct called embeddings. And these embeddings have proved to be very useful in kind of just general using deep learning with NLP in general. And so how these embeddings work is that you give it a word like, let's say, the or Python. And it takes that word and embeds it or converts it into, let's say, a 300-dimensional vector. And with this vector, people have found that they can actually take the output of this vector and put it in, use it as input into the downstream like deep learning neural networks. And they found that you could use it for things like sentiment analysis, classification, and so on. I think what's really powerful about this approach is that the vectors that come out already have some sense of like what the words mean. And so taking a numeric representation of words and feeding into neural network applications have been proven to be really useful. And so this is actually a very common pattern that you'll find nowadays with deep learning and NLP. Another quick thing is just on the ethical concerns around, I think, developing these models. And I think I touched upon it in the earlier session as well. And so here's an example of where OpenAI, they created this pretty powerful language model called GPT-2. but they actually decided not to release the model to the public because they're afraid it'd be used for like deceptive, biased, or abusive applications. And just to dive into this a little bit more on the idea of bias, there's actually been some research recently done to show that there is actually quite a bit of bias in these language models and embeddings. People found that they contain, like in this example, a lot of gender bias. And it's often because that these models are trained on text that we humans produce. And so they learn the same biases that are present in our news or our emails and things like that. And so as language models and kind of these sophisticated techniques get used more and more for things like resume screens or search engines, they can have really real repercussions for people. And so it's kind of really important to think about this particular facet of our models as well. So with that, we'll bring it back to the Twitter challenge and hopefully announce some winners.
We definitely have not gone through all of them. So give us some time. Also, let's bring up the submission slide so that.
Oh, yeah. Oh, yeah, you just have to
Okay, perfect.
So actually, I can go through some of the submissions.
Yeah.
I'll let you pick.
My favorites.
All right, yeah, so for our Twitter challenge, we have some candidates, so I'll go through some that itself. One is To Luke, Leon, and All Things by Him, Thunder, and From Earth. So like a very dramatic, I actually looked up what the
Corpus for that one
is,
was?
and it's like a Greek god, so very dramatic mythology. Brian Burgundy Mine, I hopefully stays good. Some wine reviews. So yeah, someone put in 2 Sigma trade war. We said that the agreement in good faith. Okay, good happened. Yeah, this is actually one of my favorites. I suggest buying some scented kitchen trash bags to use with this phone. It's quite extraordinary.
What's that corpus?
I actually don't know. It's similar
Product reviews for this.
product reviews.
Excellent.
Yeah, there are actually a lot of phone-related ones. Yeah, I have to open up the top 10 best-selling phones from T-Mobile. 100 times better than just gas station.
Gas?
No comparison.
There's no comparison.
And I must add to the delight / dismay of users that this phone is actually quite extraordinary. Yeah, where wilt thou lead me? Sounds like some Shakespeare. Few days. Didn't really know what to say. A few hours were to have engaged her to me forever. Very efficient dater. This is Jane Austen. Yeah, distinguished men from every section of our country, so very, yeah, I think my guess is from, actually, does anyone know?
Inaugural.
Huh? Inaugural addresses, all right. Awesome, and I think more is a bottle in his possession. Someone wants the bottle.
Wine reviews.
I think that's good.
Yeah. We still have some more coming in.
Okay. I have some candidates for.
There was one. Are we going to Las Vegas or Atlantic City?
Oh yeah.
I am pretty sure that's not coming from a computer.
Yeah, so Captain goes down with his peg leg. Las Vegas. You Las Vegas or Atlantic City? That looks like. Okay, I'm gonna spend just a minute or two to decide the winners.
Well, there's a water bottle with a keychain in it, a 3D printed one. It's not soluble. Please don't drink it with your water. I like. We should mute this.
That's okay. Alright. Yeah. Yeah. Yeah, actually,
that we took like 2 minutes to decide it. So we hadn't really gone through all of your submissions. And of course,
Oh,
this.
sorry.
Don't give it away.
Yeah, so it's kind of like apples to apples. If you know that game, it's very arbitrary on how the person picks the winner. So that's kind of what happened here too. Oh, actually, we need some
You want to maintain the mystery.
mystery, yeah. Right click.
Yeah.
Just click the right arrow.
Should I wait? Yeah.
Alright, try two.
Okay. The first one, the third place goes to a bottle in his possession.
The bottle is now in your possession. Congratulations.
All right. You want to
Yeah.
announce a second?
All right. In second place, we picked the phone-related one. I need to have a best-selling phone from T-Mobile.
100 times better than just a gas
Gas
station.
station.
There's
that
no
one.
comparison.
Okay, and for first place, we really like, I think this is probably pirate related. And it says, if the company controls the chess, they control the sea. All right.
All right. Thank you all for all the participation. We are open for. Oh, this is an important legal slide that my HR wanted. And Eugene
Yeah.
knows the gist of it.
Yeah, basically it says we're not providing any investment advice today. So, so we'd be happy to take any questions now.
Yeah. And feel free to send your questions to our email or.
Yeah, we'll be around to, hopefully you learned something new, had some fun. And,
The slides are going to be available on the website.
I
Yes.
think so, yeah.
Yes. The slides would be available, and I think it would be useful.
Are you two active on Twitter?
I personally am not.
I am Sunny. If it Sunny is a relative word.
Yeah. Just your robot is active on Twitter.
Yeah. Well, I'll retweet some of the favorites because I'm pretty sure there's treasure out there that we did not pick. Any other questions that we can answer for you guys today?
If
Oh,
not,
there's
no.
one.
Can we just use spacing? What do you think are the differences between that and system or any other?
So I'm not like super familiar with Spacey, but I think there are a lot of like nuanced differences between them. But yeah, I think I'd be happy to chat with you after about that. Yeah.
Which n-gram model is very popular? Is it bigram? Second one.
I think I'm taking an educated guess here just because like Google released their n-grams way back in like mid-90s. 4 grams were doing pretty well, but this is just me thinking from like way back. So I honestly do not know what's in the market. To be honest, it's more about neural network language models now.
No, yeah.
Yeah, and n-grams here was just to give you a flavor of like what language models really are doing. And n-grams used to be like long time ago the way of generating language models.
Yeah, and I think it depends a lot on your application as well. So kind of like if you wanted to assign probabilities to sentences, bigram language models are definitely more generalizable than let's say 4-gram or 5-gram. But at the same time, if you were generating sentences, like maybe trigram or 4-gram would give you more reasonable ones. Yeah, so that.
Yep.
Wondering where can I
the presentation slides,
Mhm.
not the notebooks. Will those be shared?
Yes, the slides will be shared.
Yeah. I think PyData, I think will be asking us for the slides and posting them somewhere. So, but yeah, so hopefully that'll be somewhere. But the notebooks, of course, will be on the GitHub.
Thank you.
How's Two Sigma leveraging NLP capabilities to work?
We will remain mute on that question.
Something that unfortunately we cannot talk about.
Give it a general direction.
Cool. If there are no more questions, thank you for all coming, and I guess we'll be here if you want any, if you have any further questions as well. Thank you.